Uh, Welcome back, Science 9 students. Today we're going to talk about energy conversions and conservation. What I have here is the Newton's cradle in front here. I'll get this thing started. This is going to be kind of the big idea of our topic, is how, well, we're going to talk a lot about the pendulum, is how the energy is being converted from one form to another. You guys know about kinetic energy and potential energy, so I'll let you guys sit and think about this in terms of converting from one form to another. I'll tell you the two key words are potential energy and kinetic energy, so I'll leave that to you guys to think about. We're going to continue on. What we are talking about today is how, like it says, big question, can energy be converted from one form to another? And the answer is yes. Energy can be converted from one form to another. The process of changing energy from one form to another is called energy conversion. So the striking of a match is another good example. Obviously, the pendulum is a good example. Energy is being converted from one form to another every time it's going back and forth. We'll save that for later. I'll let you guys sit and think about it. Let's talk about a match. This is striking. When you're striking a match, there's all kinds of energy conversions happening here. It all starts with the breakfast I ate this morning. It's taking that chemical energy and being converted into mechanical energy, where I'm going to move my hands, I'm going to move my muscles to get this thing going. And then what happens when you strike the match is this thing creates enough friction, okay, which is thermal energy. So I'm taking the kinetic energy, converting it into thermal energy, and then I'll even show you, if you generate enough friction, you can get the match to start. So now the match head had chemical energy, as you guys can see. Now that chemical energy is being converted into the thermal energy. So there it is, or the electromagnetic energy. So that energy wasn't ever lost. So the food that I ate this morning is being converted into good work here. That energy is going to be used into my muscles. Well, my muscles' energy isn't being wasted. That muscle energy is using that match, and it's going to be creating that friction, which creates enough thermal energy, which gets it to start on fire. And then the match, here you kind of see before, the match itself has potential to do energy. Well, if you created enough thermal energy, it got it to spark, and the match doesn't disappear, or the energy in the match didn't disappear. The energy in the match got converted into electromagnetic energy. So it's all being converted from one form to another. Which brings us up to the law of conservation of energy, which states that energy cannot be created or destroyed. The energy doesn't go away. Like, we have energy all around us. It's just we're going to transfer that energy from one type to another type, like you guys saw with the match. Same thing with the pendulum. It's slowing down. Does that mean that we're losing energy? I'll tell you a hint. No. Energy is going somewhere. We'll look at that later. So work done by friction changes kinetic energy into thermal energy. So if you think about friction, anytime you're exploring friction, you know, if you take your hands and go like this, your hands are going to warm up. Well, that's friction, and it's going to be converted from kinetic energy into thermal energy. Machines often, a lot of times, have a lot of friction. Air resistance would be friction. There's some air resistance happening right here, slowing this thing down. Speed skaters slow down due to friction and air resistance. All right, so now we're going to talk about what happens with energy conversions as an object falls towards Earth. So if we have this tennis ball, so like right here, there's zero energy in the system. The ball's sitting here, okay? But if I put work into the system, I raise it up to here. Now I did some kinetic energy there. So now I'm holding it right here. It has the potential to do work. And then when you drop it, that potential energy can be seen as it's going down kinetic energy. You guys know this, we talked about it earlier in the chapter. So you guys know that potential and kinetic energy, they can go hand in hand. Seagulls take advantage of this idea. When they're trying to get food out of the oysters, they'll raise it up. So they'll take some kinetic energy, bring it all the way up, get it into the potential energy, and they drop the oyster, boom, hits the rock, they got their food. All right, now let's talk about the pendulum. You guys have had to look at this for a little bit here. So in terms of energy, let's see what's happening here. When I take the pendulum and I bring it up to here, right now it has the potential to do work. When I let go of it, that potential energy is going to get converted into kinetic energy. I think you guys would agree with that. So potential to do work, I let it go. Now it's got, when it's moving, it's got kinetic energy. But let's talk about some key points on the pendulum in terms of where is the kinetic energy the highest? Where is the potential energy the highest? Is there some zeros? Do we have all kinetic and all potential? And the answers would be yes, we do have all kinds of things happening here with the pendulum. At the bottom of the swing, so if I do this kind of in slow motion, at the bottom of the swing, that's as low as it goes. And if you remember how to calculate potential energy, it's m times g times h. Well, if h is 0, 0 times m times g is 0, so you have 0 potential energy here. So if you think about the swing at the bottom, you have 0 potential energy. You're like, whoa, we lost all our potential energy. Well, no, it got converted into all kinetic energy. So at the bottom of the swing is where the pendulum is going to be the fastest. It's going to be the maximum kinetic energy. Should make sense, because here at the top of the swing, when it's, not moving, it's all potential. At the bottom of the swing, it's moving the fastest, so it's going to be all kinetic. So that's actually what's happening. On the downswing, the potential energy is being converted into all kinetic energy. And then on the upswing, it's gaining the potential energy from the kinetic energy. And then at the upswing here again, it's all potential. So if you think about it as it's going back and forth, all potential, at the bottom, it's going to be all kinetic. So this kind of puts it into words, what I was telling you. At the highest point in its swing, the pendulum has 0 kinetic energy and maximum potential energy. So at the top, it's all potential. As the pendulum swings downward, potential energy is going to be converted into that kinetic. So like it says here at the bottom of the swing, the pendulum has a maximum kinetic energy and 0 potential. I have a little video, or show you guys here. So just hang with me. So I really like this. This is a PHET, PHET simulation. It's showing the pendulum, and it's showing it in terms of, if you look over here, in terms of energy. So you have your total energy here, E total. And as you can see, the potential and the kinetic energy are just basically going back and forth and back and forth and back and forth. As you can see, the E total, however, stays the same. That's because law of conservation of energy. We're not ever losing energy. Let me try to hit stop on this thing so you guys can see it. Let me hit stop. So, oop. Or let me try to drag it, do kind of some slow motion stuff here. Oop. And I'll stop it again. So if I grab this, you can see, like right here, it's all what? Potential energy. Well, before I get it started, when I let it go, that potential energy gets converted into the kinetic energy. There's one more fun thing we can do with this simulator. if you guys notice, I applied some friction. So if you apply some friction, that's this E thermal, because remember, friction gets turned into thermal energy, and the pendulum's slowing down almost to a stop. These are getting smaller and smaller as you gain more thermal energy, but you can see from the E total that we haven't lost any energy, it just got converted to another form. In this case, it was thermal energy. So that's the basics behind the pendulum. Later on this week, you guys will be doing a pendulum lab at home, but I just kind of wanted to really show you what's going on here. So hopefully with that simulator, you guys can see this, so you can think about it. You guys know a lot more about pendulums. You got your pendulum clock here. Ooh, this is a fun example. There's all kinds of energy conversions happening here with this pole vaulter. The pole vaulter is running towards where they're going to do their jump. So they have kinetic energy. Then all of a sudden, they're going to hit their mark right here. And then they're going to slow down. So their kinetic energy is going to get converted into, this is what we call elastic potential energy. So they're running really, really fast, hit their mark. The pole's gonna gain the elastic potential energy. Then it's going to fling them up. So then the elastic potential energy is going to get converted back into kinetic energy. Then the kinetic energy is going to be converted into potential energy way at the top. And then it's going to be converted back into kinetic energy. So if you're into pole vaulting for track, that's all kinds of energy conversions happening there. So here's kind of a summary of what I was just telling you guys. Basically that kinetic energy gets converted to
Can I get all special ed teachers to the high school
elastic potential energy as the pole bends. The pole springs back into shape, propelling the pole vaulter upward. So the pole vaulter rises, his kinetic energy decreases while he gains potential energy. Then at the highest point, it's all into potential energy. Then it begins to go back into kinetic energy when he falls down. Which brings us up to the conservation of mechanical energy formula. Which you guys know, you saw with the simulator, is that these two at the beginning added together equal these two at the end. You guys saw that with the simulator. The E total didn't change. You got a little bit of both. So we're gonna use this formula to solve a variety of problems. So it says at a construction site, a 1.5 kilogram brick is dropped from rest and hits the ground at a speed of 26 meters per second. Assuming air resistance can be ignored, calculate the gravitational potential energy of the brick before it was dropped. Alright, so here's what I like to do when I'm solving these problems, is I like to do a before and after picture. So we have a brick before it's dropped, and then we have a brick after it's dropped. We know the mass of the brick is equal to 1.50 kilograms. We know that the speed down here, so the V final, we'll call it the final speed, is going to be 26.0 meters per second. We know the initial speed over here is 0. Okay, that's about all we know right now. Let's write down our formula. So we have the potential energy plus the kinetic energy at the beginning equals the potential energy and kinetic energy in the end. With these problems, you're looking for zeros because you have 4 terms in these ones. So if we can cancel out a couple terms, it makes our life a lot easier. So let's think about this. At the beginning here, the velocity is 0. Okay? So if the velocity is 0, where it's not moving, so then technically we don't have any moving energy at the beginning. So there's our first zero. So I'm going to go like that. And I'm just going to plug in a zero. So this term is a zero. Now, when it's down here, do we have any potential energy? And the answer would be no. So the potential energy at the end is also going to be a zero. So now we have a new formula. Because we eliminated a couple terms, we have the potential energy at the beginning equals the kinetic energy in the end. And actually, instead of, I'm going to call this final and initial. I just like those terms a lot better. So potential energy initially equals the kinetic energy in the end. We can expand this out to mgh equals 1/2 m, we'll call this Vf squared. So now we have a new formula we can work with. And it's saying, what are we trying to find here? It says calculate the gravitational potential energy of the brick before it was dropped. So we basically want to calculate this. Well, this essentially equals that, the Kf, so really I didn't have to expand this one out. I'll change that back. So really, the potential energy at the beginning equals the kinetic energy in the end. So now we can just plug in our values. So 1/2, we know m is going to be 1.5. And we know velocity is 26 squared. So then we'll just solve that. We have 0.5 times 1.5 equals that times 26 squared. And I get potential energy in the beginning equals 507, and that's going to be joules. So there it is. So the big trick to these problems is to kind of sketch it out or kind of have it in your brain. So I did my quick sketch so I could see what was going on. And then the second part is find your zeros, because if you identify your zeros, you can really make this formula a lot easier to work with. So let's try another one. Practice makes perfect. So let's look at this one right here. We have a 10 kilogram rock is dropped and hits the ground below at a speed of 60 meters per second. Calculate the gravitational potential energy of the rock before it was dropped. Alright, so we got a rock. So I'm going to do my before and our after drawing. There's the rock down here. We know the VF is 60. We also know that the mass of the rock is 10. Okay, and that's what we know. Let's look at our formula. So we have potential energy plus kinetic energy. Initially, I'm just going to put an I there, equals the potential energy plus kinetic energy in the end. So final. And then I'm going to identify my zeros. Well, with this problem, before it was dropped, we don't have any speed. So the initial kinetic energy is 0. It's like if I have this right here, do I have any kinetic energy? The answer would be no, right? But when I drop it and it hits the ground, do I have any more potential energy? The answer would be no. So there's my two zeros. I have a new formula. We have potential energy at the beginning equals the kinetic energy in the end. The problem's asking us to calculate the potential energy. Okay, so I'm just going to leave this term alone. I'll expand this term out, and I'll call it VF squared. And it's just like the last problem. We just plug in the mass, we plug in the velocity squared. So then 1/2 times 10 times 60 squared. So we're going to go 0.5 times 10 times 60 squared. And I'm going to get 18,000 joules. So there it is. So yeah, these problems, don't panic. Identify your zeros and then just kind of plug in what you know. Like, and if you have to, find a ball, think about it, go, what's the kinetic energy at the top? You should know that's 0. When you drop it, okay, what is the potential energy down here? Well, that should be 0. So if you have to run through these problems, really think about them, that's going to be the key to solving these. Alright, let's try a couple more. So now we have a diver with a mass of 70 kilograms, stands motionless on the top of a 3-meter high diving platform. Calculate his potential energy relative to the water surface while standing on the platform, and his speed when he enters the pool. Alright, so we'll draw in a diver here. There we go. It's on a platform, it's gonna jump into the pool. It's going to be height equals 3 meters, we know that. Let's see here, we know the mass is equal to 70 kilograms. So again, I like to draw out a sketch so that I can understand what's happening here. Then obviously he's going to jump into the water. So alright, I think I got an idea here. So I have potential energy plus kinetic energy initially equals the potential energy plus the kinetic energy in the end. So let's think about the zeros. It says motionless, stands motionless at the top. Well, that's a clue. That means that initially we have 0 kinetic energy. Okay. Now, when he hits the water, he's not going to have any more potential energy. So that's also 0. So we have a new formula that we're going to work with. We have potential energy in the beginning equals the kinetic energy in the end there. It is asking, this question is asking us to calculate his potential energy relative to the water surface. Well, we can do that. We don't even need the formula to do that because potential energy is equal to mgh, and we have the mass, that's 70, gravity is 9.8, and the height is 3. So really, that's just a formula that we've used earlier in this chapter. So 9.8 times 3. So his potential energy is 2,058 joules. So again, I'm going to stop. We were able to solve potential energy without that formula, okay? Keep that in mind. Because potential energy is mgh. Well, we have mass, we have gravity, and we have the height. So we can calculate that without using this formula. And that's going to be important. Now the next part of this problem says, find his speed when he enters the pool. So this is going to be one answer to it. The next answer is finding his speed. Okay. Well, guess what? We just calculated the potential energy, so we can plug that number in for potential energy. Okay. Let's expand this out. 1/2. Well, it's 1/2 mv squared for kinetic energy. That's the formula. We know the mass of the diver is 70. And then we're trying to find his speed when he enters the water. So that's going to be v squared. Okay. So then I'll just take this. So v squared equals 58.8. Is that how fast he's going? Hopefully the answer you guys are saying is no, because we still have to take the square root of it. So then second. Okay. So then v equals 7 points, and let's just round our number to the nearest tenth, 7.7 meters per second. So there's the answer right there, 7.7 meters per second. And I think what I'll do is I'll let you guys try this one on your own, and then we'll call it a wrap. So you guys will have a Schoology assignment with 15 2 energy conversions.